My name is Srinivas Govada. I am working as an assistant professor in IARE college. Today we will discuss about the DBMS deadlock. In a multi-process system, deadlock is an unwanted situation that arises in a shared resource environment. In a multi-process system, a deadlock is an unwanted situation that arises in a shared resource environment where a process indefinitely waits for a resource that is held by another process. So deadlock is nothing but it waits indefinitely for some other resource, because that resource is being used by some other process. For example, assume a set of transactions T0, T1 to T10. T0 needs a resource X to complete its task. T0 needs X to complete its task. But the resource X is being held by T1. And T1 is waiting for the resource Y, which is held by T2. T2 is waiting for a resource Z, which is being being used by T0. So, thus all the process waits for each other to release resources. So, T0 needs X. X is being used by T1. T1 needs Y, and T2 needs Z. And this Z is being used by T0. Now, everything is in a loop. And everything, so nothing will succeed because everybody is looking for a resource which is being used by another resource. So thus, all the process wait for each other to release resources. In this situation, none of the process can finish their task. This situation is known as deadlock. So this is called deadlock. Deadlocks are not healthy for a system. In case a system is stuck in a deadlock, the transactions involved in the deadlock are either rolled back or restarted. The deadlocks are not healthy for a system. In case the system is stuck in a deadlock, the transactions involved in the deadlock are either rolled back or restarted. Now, we will see how can we prevent a deadlock. To prevent a deadlock situation in the system, DBMS aggressively inspects all the operations where transactions are about to execute. To prevent any deadlock situation system, DBMS aggressively inspects all the operations where the transactions are about to execute. The DBMS inspects the operations. DBMS inspects the operations and analyzes if they can create a deadlock situation. So DBMS will inspect all the operations and analyze if there is any chance of deadlock. If it finds a deadlock situation might occur, then the transaction is never allowed to be executed. See, the DBMS will inspect all the operations where the transactions are supposed to be executed. If there is any chance of a deadlock, the DBMS will never is allowed to execute. The DBMS will not allow the transaction to execute. There are deadlock prevention schemas that use timestamp ordering mechanism of transactions in order to predetermine a deadlock situations. So there is something called as timestamp ordering mechanism of transactions in order to predetermine a deadlock situation. One is wait die scheme. In this scheme, if a transaction requests to lock a resource, the transaction is requesting a lock on resource X, which is already being held with a conflicting lock by another transaction, Then suppose you want to lock an item X, but this X is already being locked by one more transaction T1. T0 wants X, but this X is being used by T1. Then here there's two possibilities might occur. Timestamp of T1, Ti is less than timestamp of Z, which is second one thing. That is Tz, which is requesting a conflicting lock. Ti is requesting a conflicting lock is older than Tz. Ti is requesting a conflicting lock of X, which is being held by Z. If Ti is older than Tz, then Ti is allowed to wait until data is available. Okay, if timestamp of T1 less than timestamp of Tz, that means that is older than Tz, then T1 is allowed to wait until the data is available. However, timestamp of T1 greater than timestamp of Z, that is T1 is younger than Tz, then T1 dies. T1 is restarted later with a random delay, but with the same timestamp. The scheme allows the older transaction to wait, but kills the younger one. The older gets the preference, but the younger will be killed. That is wait die scheme. Let us see one more scheme. What is wound wait scheme? In this scheme, if a transaction requests to lock a resource which is already held with conflicting lock by another transaction, one of the two possibilities may occur. In this scheme, if a transaction requests to lock a resource, which is already held with conflicting lock by another transaction, the one of the two possibilities may occur. If timestamp of T1 less than timestamp of Tj, then T1 forces Tz to be rolled back. That is, T1 wounds Tz. Tz is restarted later with a random delay, but with the same timestamp. Okay. If Ti is less than Tz, T1 forces Tz to be rolled back. That is, T1 is wounds Tz. Tz is restarted after a random delay, but with the same timestamp. If Ts of T1 Ti is greater than Ts of Tz, then T1 is forced to wait until the resource is available. This schema allows the younger transaction to wait, but when the older transaction requires an item held by the younger one, the older transaction forces the younger one to abort and release the items. In this scheme allows the younger children to wait, but in the earlier case, the younger transaction are killed. But here they can wait. But when the older transaction requests an item that is held by the younger one, the older transaction forces the younger one to abort and releases the item. In both the cases, the transaction that enters the system at later stage is aborted. In both the cases, the transaction that enters the system at a later stage is aborted. This is wound wait scheme. Earlier we have seen wait die scheme. We also seen wound wait scheme. Now, how can we avoid a deadlock? Deadlock avoidance. Aborting a transaction is not always a practical approach. Instead, deadlock avoidance mechanism can be used to detect any deadlock situation in advance. Methods like wait for graph are available, but they are suitable for only those systems where transactions are lightweight, having fewer instances of resource. In a bulky system, deadlock prevention techniques may work well. Methods like wait for graph are available, but they are suitable for only those systems having lightweight, having fewer instances of resource. In a bulky systems, deadlock prevention technique may work well. Now we'll see what is a wait for the graph, which is used for lightweight transactions. This is a simple method. It's a simple method available to track if any deadlock situation may arise. This is a simple method available to track if any deadlock situation may arise. For every transaction, entering into the system, a node is created. For every transaction entering into the system, a node is created. When the transaction T1 requests a lock on item, say X, which is held by some other transaction Tj, a directed edge is created from T1 to Tz. So if Tz releases an item X, the edge between them is dropped, and T1 locks items. See, T1, T2, Ti, Tz. Yeah. See, now Tz is using Tz. Now here, wait for graph. There's an edge is created between T1 to Tz, and Tz releases the X immediately. This edge is dropped, and T1 locks the item X. This system maintains this wait for graph for every transaction, waiting for some data held by others. The system maintains the wait for graph for every transaction, waiting for others data item held by others. This system helps checking if there are any cycles in the graph. Here we can use one of the following approaches. First, do not allow any request for an item which is already locked by another transaction. He says that do not allow any request which is already locked by other, but this is not always feasible and may cause starvation. That means you will never get that. You will never get it. Where a transaction indefinitely waits for an item and it never requests it. It says that do not allow a request to something you use somebody else. This is never possible because you will never get it. The second option is to roll back one of the transactions. It is not. Have you ever seen that the younger one is always killed or aborted? The second option is to roll back one of the transactions. It is not always feasible to roll back the younger transaction, as it may be important than the older one. With the help of some relative algorithms, a transaction is chosen which is to be aborted. This transaction is known as victim, and the process is known as victim selection. So here T1 is waiting for X and Y also is waiting for X. Waits for locked Y, waits for T1 is waiting Tz. Now both are waiting. So at there, this is so due to now victim selection and the one of the it is aborted, the rest can proceed. With this, the deadlocks scenario is completed.
Like, share and subscribe. Hit the bell icon for more updates.